Hi. This week we are actually going to take a look at the molecules which are our semiconductor, and we will try to have a look at it as a collection of springs. If you would like, you can imagine it like this old-fashioned bed. And one of the things we'll be asking ourselves that once we have a film made of springs, is it really easy to move across such a flexible substrate? The other deep question you may find asking yourselves today or during the course, are you one of those who can really handle only stiff and hard things, or you can also be a bit flexible and handle the uncertainty that comes along with flexibility? So such deep questions are going to be part of today and the next few lectures. So basically the springs, as we've mentioned before, these are polymers or small molecules, and these are the examples I brought before, the historic ones if you like. This is the polyacetylene that showed the transition from insulator to conductor and was awarded the Nobel Prize, or to be more exact, the three that discovered the phenomena was awarded the Nobel Prize. MEHPPV used to be the prototypical OLED material, and TPD used to be very famous in small molecule OLEDs. So really, we are going to try and see the idea of these bonds acting as springs in affecting the performance of the materials. So really, to be a bit more exact, we are really interested in seeing the fact that the material is being soft, how would it affect the electronic properties? And I've already introduced this old-fashioned bed. And one of the things you need to ask yourself, if you are already convinced that this could be a model, why should it be this kind of old-fashioned model? Why can't we use this type of spring bed to describe what's going on? And the deeper question is which one is better suited for this lecture, and I'll let you decide upon it as we go along. It looks like a bit of nonsense, but there is some deep differences between these two beds, and they do reflect in the electronic properties. So let's discuss again level formation for two p orbitals, and we are going to discuss this orbital considering the fact that it has also a phase. So if we have two of them, we can have two combinations. One of them is where both orbitals are in phase, and the other one which they are out of phase. Naturally, if they are out of phase or in phase, the interference would be different. If they are out of phase, then obviously in the middle they are equal but of opposite sign, so there will be 0. However, if they are of the same sign, there would be some positive interference, and we will describe the wave function schematically like we see here. So basically what we find is that for this form of the wave function, there is an extra negative charge in the middle, and we have this arrangement of plus minus plus, which we know is attractive. On the other hand, the one that is above it doesn't have this feature. So we know that when we have such plus minus plus, it tends to stabilize the structure. And if something is stable, then it is of lower energy. And that's the reason why I've already arranged them, this one below and this one above. As far as names, we call this one bonding, the one at the top anti-bonding. Why it's anti anything, I have no idea, but that's the name. If you prefer, just use pi and pi star. So basically we have one stable and one less stable state. So this is for two atoms. So let's try and expand it a bit. Now we take 4 orbitals. And again, I've arranged them here, and the colors are for the phases. So you see the bottom level is when everything is in phase, and as we go up, there are less orbitals in phase, and the topmost one, they are all out of phase. So if we have 4 orbitals, we have 4 electrons, and where would you suggest that these 4 electrons should reside? So basically we are talking about relatively not very high temperature, so things are at equilibrium. And we see here that as every level can occupy 2 electrons, we have maximum 4. So will be 2 here and 2 here, so we'll have 2 occupied levels and 2 empty levels. And of course, once we have 4, we can say that this one is the highest occupied molecular level, and this one would be the lowest unoccupied molecular level. So in short, this one is the HOMO, which would be the equivalent to the valence band in the standard semiconductors, and this one would be the LUMO. The other thing that I've added here without mentioning is the idea that if we have a stabilized bond, then the distance is going to be shorter. So you can see here that there is already some relation between the electronic configuration where the electrons are residing and the shape of the molecule. Because at present, when it is in the ground state, then the shape of the molecule has to be some kind of a combination of these two configurations. Of course, if we will invest some energy and this electron would move up, then we will have also to consider this one, and that of course will change the way the molecule looks like, or it will change its shape. So this is really schematic, lots of hand waving, but you can already see that there is some kind of a relation between the configuration coordinates, or the way the molecule looks like, and where the electrons are residing. And this is going to play a very important role as we go along. So if we try to place it on a graph, and of course things are not going to be to scale, it's just to illustrate the idea. So we have these 4 configurations, and we'll call them the configuration of the coordinates, or coordinate configuration. And we see that each of the levels has a different energy. So now we are going to consider what's going to be the energy of the molecule. So we are now going to look at the configuration coordinates, which be the x-axis, and we already know that if the molecule moves from the ground state to the excited state, it has to change its shape. So if it's changing shape, we are moving right or left on this configuration axis. Of course, because it was excited, then it has to be higher in energy. So really this is the ground state, and the first excited state in a soft material is shifted slightly to the side. Now we know that these are soft, so if they are soft, then the molecules are changing. You see this one started this motion, which of course, I remind you, this is PowerPoint. This has nothing to do with reality, it's just to give you some kind of intuition. So if it is breathing a little bit and it's changing, then we already know that the electronic level has to change, So the actual energy is going to change due to this motion. And what we will find is that there is this kind of something that looks like a parabola that the molecule travels along. So as the molecule changes shape, if it moves from its equilibrium, then it will contain a little bit more energy as the shape is changing. And of course, the same thing holds for the excited state. And this is a very famous graph of soft materials for the configuration coordinates, where we see the ground state and the first excited state. And this shift either right or left is really the manifestation of the link between the configuration and the energy of the molecule. So what we see typically in real molecules, this is just an example of a certain molecule which you can find in the literature. And you can see that there are two semi-stable states. One of them is the true minimum. But the reason I bring it here is that if you look at it, you see this is not a parabola and this is not a parabola. The idea that allows us to treat this like a parabola is that basically we are always interested in very small changes in shape. So we're really looking at the very, very bottom of this graph. And if we zoom at the bottom, then we can approximate it rather well like a parabola. Why do I say rather well? Because the notion of using a parabola to describe it works well and allows us to make sufficient progress in theory and understanding some of the experimental results. So if this is a parabola, we know that at least in basic physics, we've already seen something that has this kind of shape of potential that is associated with shape changing, and this is the spring. And this brings us to the idea of a molecule as a spring, and we are going to continue from now having in mind that when the molecule changes its shape, it stretches or contracts, the potential is going to change similarly to what would happen to a spring. And if you would like, we are thinking of the bonds between the molecules as springs. So basically, this is it. What I just said, just graphically, on a PowerPoint level, this breathing is like the spring being elongated or contracted. So we are now dealing with springs, and we want to deal with energy, or to discuss the energy of the molecule or the spring. So we have to ask ourselves, okay, we have a molecule or a spring at a certain configuration. This is like the resting state of the spring. And we know that its energy is associated with its constant that we'll call its B, how much it's being distorted from its equilibrium state. And of course, there is always some kind of a background energy that would be associated with the place where we've hung this spring. So if you hang it on the first floor or the 10th floor, you could say that there is some different energy between the two, especially if you try to drop this spring on someone's head, of course. So let's look at this spring, and we'll slowly develop this picture and see where it takes us. So really, we are thinking of this elastic potential of being similar to the molecule, where either we have reduced its size, or the links here became shorter or longer. Of course, in real molecules, they are 3D, so everything is happening in 3D. Changes in shape are not just in one direction, but for simplicity, this is what we are going to consider. And because I haven't managed to find a 3D screen, we will continue using this simplistic approach where all the configuration coordinates are allowing us to form just a 2D map. So really this is the elastic energy of the molecule or the spring. And the spring constant is B. So we have our molecule, which essentially it's a spring, and we are going to follow how it behaves when it's being excited. So in order to excite a spring, what we need to do is to somehow find a mass and add it to it. And once we've added a mass to the system, then the overall energy has changed. And before we had only the energy of the spring, now we also have the energy of the mass, that for the spring it is mgh. And really what we are seeing now is at t equals 0, the mass has already only entered the system, but nothing has happened. And of course, we would expect that the next thing that would happen is that there will be some kind of relaxation. The coordinates of the spring would change, and that means that the energy of the spring would increase. The energy associated with the mass, of course, is going down, so we have something that goes down, something that goes up. But because there was a spontaneous transition from this state to this state, then we can safely assume that the overall energy here is lower. So this is really, if you like, we follow the states of ground state, excited state, and excited state after relaxation. And this is for a 1D spring. And we've already considered the 2D spring, if you remember the guy on the trampoline. And I bring it here again, simply so you'll see that on 2D it looks as if the particle has dug itself a hole. So let's now talk about the configuration coordinates and the energy potential of these springs. So we know we start with the spring, which is not excited, so it has its ground state potential, and we know that if we pull or push the spring, it will change its potential according to this formula. The next thing we know is that if we take the mass and we add it to the spring, then the overall energy would go up. This is like our mgh. And if we would change the shape of the spring without the mass moving at all, which of course is not possible, but you can imagine that the mass is staying at its position and only the spring has moved, you will get this non-realistic reference potential. But we know that in fact what will happen is that as it moves to the right and the spring becomes longer, then the overall energy goes down. And what we found ourselves is that we have this kind of a potential. And here you see what I've discussed before, that the excited state is of a higher energy, but it's slightly shifted in the configuration coordinates. And in our case, the configuration coordinates is simply the length of the spring. And the minimum coordinate is now different. So before we defined the 0, and now it has moved. And what we will try in the following is to use the notion that we can characterize the molecular spring. And with that, we would like to understand how these potentials are shifting to the right, etc. So before we do that, just a little bit some extra intuition to those that this would help them build one. So if you've encountered quantum wells before, which I'm sure you have in one way or the other, then you know that there is this first level or a higher level, doesn't matter. And if the molecule or the quantum well is being stretched, then the level would go down. And that's really similar to what we've seen before, because once we stretch, the energy of the electron that was here has gone down because the electron has shifted. If you would like, you could take the energy that we know that describes the expression that we know that describes the energy, you take the derivative, and we get that there is a linear relation, and this is like the factor that controls the change in energy. And the fact that it is linear is something that we are going to use because it is common to define the electron-phonon coupling, the idea that stretching changes the electron energy by a multiplication by something that we will call A and the coordinates. And of course, if you think a bit more carefully, then me convincing you that there is a linear relation is of course cheating without any shame behind it. Because really, anything you take a derivative of, or first derivative, of course, when you approximate it this way, you will get something linear, right? So I'm sorry, but that's the simplest and easiest way to convince you that this is what it is. And this constant is usually something like 0.1 angstrom per electron volt. And this really shows you that really the changes in the molecular structure are going to be minute, although the effect on the energy is going to be noticeable. So really, what we are dealing with this set of energies. We have the electron-phonon coupling, which is the stretching and the shift of the level due to that. And we added it to what we had before. We have the background energy, the elastic energy of the spring, and now we have the electron-phonon coupling that adds to the equation. And if we put them all together, we have the background, the B, and the A. And really, we shouldn't forget that the background is really composed of lots of different contributions that we are not going to get into them, partly because I don't really know all them. So better not to start. So really, this is our picture. This is, if you like, the potential that we know that is not realistic because there is no electron-phonon coupling here. And this is the real one. And usually when we discuss such systems, we take the difference between the system without electron-hole coupling and the system with as being important. If you like, we never knew that there could be some kind of a coupling like that. And what is really important for us is how our system, being soft, is different to other systems which are not, or something like that. So we defined this as the EB that will later on take the form of some kind of a binding energy. That's the reason why we have this B. So if you would like to find this B, it is equivalent to finding this Q min, because everything here is known. We know the parabola and the A. So really this is expressed here. When we plug it into the full expression, we take a first derivative, we solve it, and this is the energy. And we might remember that on the way we found the minimum coordinate, or by how much the coordinates have shifted, or how much the molecule changed its shape. And what is important for us is that we see here stabilization, and stabilization is often taken as some kind of binding energy. So we've talked so far, but we started the lecture with rolling a ball over the bed, which was some kind of indication that we are going to discuss transport. So how does all the above relate to charge transport? Because really our goal is to find an expression. We want to know what would be the rate. We have an electron on one molecule. We want to shift it or to move it to the next molecule in line. And we want to know what's going to happen. How would an electric field affect the situation, etc. So really this is, if you like, the plan for the next slides.